All right, let's start with a small recap from the last sessions.
So
During the first session, we went from a very simple program and we transformed that into matrix multiplications. We mentioned that this is similar to a hash. We did a small softmax generalization there. This is an attention mechanism. Went from there to build a block that we could use. We learned a bit about encoding, byte pair encoding for tokenization. We learned a little bit about embeddings and how to train them using a large corpus of data and some of the properties they had. In the second part, we did a language model instead of a translation problem, and we had a sliding window through sentences to predict the next word. In this example, we showed how the information propagated through the network, how to build a small language model with the attention that we did before. Some boilerplate code to do a tokenization, data set, typical training loop, and to use the model after training. And then with that, we started to do our first language model, which was kind of a disaster. We realized that we needed some mechanism to avoid the network from cheating, and that is the mask attention. Once we add that, the network starts learning a little bit better. Then we added some other things like multi-headed attention. We added positional embeddings. We added a nonlinear layer, then put them in a block and we stacked them. We had a deep network, so use some of the standard techniques to make sure that we can train it properly, like doing residual connections and layer normalization and dropout, etc. We use this multi-headed attention and feed forward. We built it a language model. Once we had this version of the language model, we just scaled it a little bit and it learned reasonably well. In the third installment, we installed in an EC2 instance a model installing the CUDA drivers. We installed the Llama model and we tested it. We talked about the transformer, the encoder and decoder side, revisited the translation part and show how this was done in the model by feeding the input and then doing a loop in the model, feeding each word, predicting the next one. We talked about contextual embeddings, and then we mentioned the difference between pre-training and training, because after learning the language, the model might not do exactly what we want. So we need to train the model to answer our instructions, and this is done using a reward model. After that, you might want to fine tune it with some specific tasks, and the problem is that you need to fine tune the whole model, but there are adaptation mechanisms. We learned about LoRa, where you use a lower rank to learn, so it's easier to train and adapt instead of fine-tuning the whole model. We talked about generative retrained transformers and the model scales a little bit. We talked about the emerging behaviors that you see when you scale the models. Also talked about the open source LLM. And in this part, we're going to talk about prompts. Just to recap from the model that we have an input and you run it through the model and it gives you a prediction for the next word, which then you put back into the input. So from our perspective, what you have is a block that is the LLM, you have an input and there's an output. More generic would be that you have a set of tokens and there's a prediction of the next token in the series. The prompt is all you have for the input to the LLM. Given that this is the only input, in some way, the only API that you have to interact with an LLM is the prompt. How big is the prompt? Well, the average page is usually around 3,000 characters or 500 words. For English, one token is approximately 4 characters or 0.75 words. So for a 4K token, this is roughly 5 pages. 8, that is 11 pages. And for a 32K prompt, we're talking about 45 pages. So you can squeeze a lot of information in 45 pages. So we have plenty of room there, and there are techniques when this is not enough. A typical example of what happens is that you have a prompt like the sky is, and you expect the model to just answer the sky is blue, for instance. And what you get is something like the sky is blue on a clear day, on a cloudy day, the sky might be gray or white. And this is not exactly what you intended to do. So how do you guide the LLM to do what you want? The other problem that you usually have is that you have a chat model where you have several inputs and outputs from users and the answer from the system. So maybe you started with this, and this is what the system answered, and then you reply with this, but it's not clear whether the input was provided by the model itself or not. In those cases, you could add roles for different parts of the message. So instead of just giving the model this thing without any information on who said what the models usually have is some predefined roles. You, for instance, specify, okay, user, this is what the user said, assistant is what the model reply, and user, this is your answer. So you can hint the model a little bit more on what part of the dialogue was from each side. But there are other things you can do with the roles. There is a role, for instance, called system. You can give the model some instructions or guide the behavior, and we're going to see some examples of that. There is a role user for what the user input is, and there is a role assistant for the answer from a previous conversation. You can also obviously insert whatever you want in the prompt. So you can put something that is actually made up by you as an assistant role in order to guide the model further on how to do that. And we're going to see some examples of how that sometimes helps. And then there's something which is a function. You can ask the model to say, generate a function call. And this is a concept of using tools in general. So basically, you can say to the model, these are the tools you have available. Tell me what you could do next. And the model would tell you, well, I need to use a calculator and calculate this or stuff like that. Or I need to use a search and Google this, whatever. Here's an example of the roles. You say, as a system, you will be provided with statements, and your task is to convert them to standard English. And here's a sentence in not so great English, and here is how it was modified to make it better by the model. Another example, and again, these are all trivial examples that you can find at the OpenAI website. But as a system, you send summarize this for a second grade student, and you send some text about Jupiter, and then the system answers, the LLM answers this response. Some techniques that are used in prompt engineering, there are many of them, but some of the techniques you will hear very often are zero shot, few shot, chain of thought, and so on. We're going to take a look at a few of them so you have an example of what they mean. Zero shot refers to the ability of a model to learn without giving the model any information. You are not giving any examples or any data or what needs to be done, and the model knows or understands what needs to be done. In this example, you're saying, classify the text into neutral, negative, or positive. And here's a text. I think the vacation was okay. And the answer of the model is neutral. So we did not give the model any kind of example about this. The model inferred this directly just from the description of the task. And this is called zero shot. In some cases, instead of giving no information, you can give an example to the model because that makes the model behave better. So here is an example where you have some word, and it says, here's a definition of the word. Here's an example of a sentence, gives another word. It gives a definition of that word. It says an example of the sentence that uses this is, and the model answers that. So here is a few shot because we gave the model one or maybe a few examples from the prompt itself. Use that knowledge to answer the instruction. There's another prompt engineering technique called chain of thought. In this case, the input to the model is this whole thing. So you start with a question, show another question, and get from the model the wrong answer. If you give the model an instruction that includes a detailed answer, then the model answers using the reasoning example as well and answers the right now. People say you let the model think. It seems to improve for this kind of reasoning. There are several extensions of this chain of thought prompting, one called tree of thought, trying to do some kind of exploration or look ahead. Here is the typical example where you do an input and output prompting. You basically said, tell me something, and the model outputs this. The chain of thought is what we just saw. You ask the model to explain each part of the reasoning step by step, and this seems to improve in some cases. There's another which is called self-consistency, where you ask the model several times, and then you do a majority vote. And tree of thought is where you are basically doing tree exploring with the model, and you're using the model itself to rank the answers and to see what you should do next in the tree. So let me explain how this works. First, you ask the LLM to create the first thought in the reasoning. In the example that we had before, you could ask the LLM to say, okay, only give me the first part of the reasoning. And you do this several times. You have maybe different answers. Or maybe these ones are good and these ones are bad. Then what you do is you ask the LLM to self-critique. So you say, this is a task. This is the first step that you would take. Do you think that this is good or bad? And the LLM will tell you whether it's good or bad in some kind of score. And then you use that self-critique to select the ones that are rated as the best ones. And then you feed those to the LLM and says, okay, given this problem and the first thought, what will be your next step? And then you use this iteratively. You use the LLM saying, okay, self-critique this, then you select the ones that go next, and you discard the other ones that are not so good, and so on. So until you get an output. So you iterate and you explore the whole tree until you reach an output. I think one of the interesting parts here is that you're using the LLM to give you the first step and then to say, was this a good or a bad idea? And then you use that as a scoring mechanism. Which of these techniques are applicable for your particular case? Obviously, you have to explore which one is more useful for different cases. Even in the paper where they explain the tree of thought, they have to help the model a lot in order to get the results that they want. So these techniques are, although they are meant to be generic, they are sometimes not so generic as they claim to be. At the end of the day, the way that we interact with these LLMs is, as I mentioned before, is through the prompt and using an API. And this is an example of what the API for OpenAI looks like. And you basically select, you send some parameters like your model, and you send the messages, and each message has a role, has a content. The role is the ones that I mentioned before, like a system, user, assistant, and so on. The content of the message, and you have a list of them, and some other parameters like, you know, the temperature and other parameters that you can set. So you can send an API call, just using curl if you want. And that would be the way to interact with these models in most of the cases. If you create your own model in an EC2 instance, then what you need to do is to put a small API in front of it to actually do something like this. And I think in the repository, I have some code with a small example of how to create that API. And there is also a standard Python package that is released by Hugging Face, where they have a more sophisticated API that you can just plug a model in and do some of these things. You don't have to rewrite it from scratch using Fast API or something like that. We mentioned about function calling, and this is kind of a weird concept. This is somehow related to this chain of thought that we were talking about before. In some cases, what you do is you ask the model, okay, this is what I need to do. Here are the tools that you have available. Tell me what would be your next step. And in some cases, that step could be, oh, I need to calculate something. I need to search for something, and so on. Now, this was a little bit more formalized with this function call that was introduced recently for the OpenAI models I'm talking, but other models do have it as well. So the idea is that you can tell the models to output a JSON object containing arguments and call to functions. You describe the functions. For instance, let's say you have a function that says send email, and you describe what the function does, and you describe what the parameters are. The LLM will tell you, okay, I need to call this function. On your side, you do the function call, you get the result, and you feed that back to the LLM, and it says, okay, here is the result from that function. And the LLM, based on that, continues the reasoning from that. So the interaction is not that you just send one API call and you get the answer. It's more like you send an API call, the LLM says, I need to do this. You have that function implemented on your side. So you call that function with those arguments, get the results, feed it back to the LLM, and so on. So here's an example of this. And again, this is a toy example from OpenAI's website. Here is a function that is called get current weather. And it's just hard coded. For the sake of this example, it basically returns a JSON with some weather information. You have the messages, the user role, and the content of the message is what is the weather like in Boston? And you have the functions defined here. The name of the function is get current weather, a description of what it does, and the parameters, location, and unit, and so on, which are the parameters that you have here, location here, and the unit here. So you create a request to the model, you specify which model you want, you specify which is the message that you defined here, you specify what are the functions that you have available that you have here, send the message. Once you do that, you get a response. And from the response, there's a specific part of the message that is called function call. You get that part. And from all the functions that you have available, in this case, there's only one, but maybe you have many. So you just invoke the function here, and then you have that response. You append that response to the message, and you send that back as another request to the model. You send those messages back, and then you get the final response from the model. So this is an iterative way of calling the model. Now, this is a little bit involved. To do this is a little bit low level. You have to craft the messages, you have to send the JSON messages, and so on. It's doable, but it would be nicer if we had a framework that allows us to do this. And that framework is called LangChain. This is, I think, one of the most popular ones. LangChain is a framework to develop applications powered by language models. So it lets you build an application, and the application combines different elements that are in the LangChain framework. You have LLM, which is a representation of the language model. This is an object that takes care of doing the interactions with the real language model. It abstracts all the interactions and the API calls and all that for you. And then there are other elements. We're going to take a look at them in a little bit more detail. Here's a trivial example. Import this object, which is a chat for OpenAI, create an object. And then you have some text that you want to send, and you call predict for that text, and it gives you, the model gives you this output. In the sample code that I have in the repository, I have an example where you can create your own language model object. So what I did there is you have an EC2 instance with your own model running. I mentioned before that I created a small fast API backend, and then with a small class that I created also as an example, you connect to the LLM in an EC2 instance. So there's a code example in the repository for doing all that if you want from scratch. If you're curious on how to implement that yourself, you can take a look at it there. And what are the key concepts in this framework? We have LLM that represents a language model. Memory just represents your interactions with the model. Obviously, you have to store those interactions somewhere, and it's what they call a memory object. A prompt template is just a template for a prompt. So we're going to see an example right now. And then we have other things that are output parser, chain, tools, and agents. And we're going to look into examples of this in a couple of minutes. So the core object is the LLM. This is just an object that has all the basic parameters and interacts with the API of the language model. The prompt template is a very simple concept. Here is an example of sentence, and you have a part of it that is variable. You have some text and some part of it that is variable. You can use that to put different values in that variable part. That's it. So it's a very simple concept. And the Once you get the output from the LLM, you might want to parse it in a special way. Sometimes you tell the LLM, give me a comma separated list of values, and then you have a comma separated list here. Maybe you want to parse the list in a specific way. So here's a trivial example, again, from the LangChain website, where it parses the text and converts that into a list. In general, you don't need to write your own parsers, but for specific pipelines, you might want to. The memory concept, as I mentioned before, is just somewhere to hold your conversation. So here's the usual interaction. Basically, you have some user input. The prompt generates the text, what is going to the model. This obviously goes and makes the API call, and the answers come back. And then you have an output parser that parses the output, and that's stored into the memory, so you can use it in the next step of the conversation. The next concept in LangChain is the concept of a chain. Now here, a chain is a very simple set of items that is together. You have an LLM, you have a prompt template, and maybe an output parser, and they're put it together, and this is called a chain. And the idea is that you can have many of these chains, and you can also do chains of chains. So you can make it a little bit more complex, and you can nest them. An example of this is what we saw before. For instance, we have the comma separated parser that we saw in the previous slide, and we have a prompt template. And here is saying you're a helpful assistant, we'll pass a category, and you should generate 5 objects in that category, comma separated list. So the chain is defined as having an LLM, the prompt, and it's also having the output parser that was defined here. And so the chain has these 3 elements and combines them, and basically when you run it with an input, it puts that input into the prompt. It sends the prompt to the LLM, parses the output, and gives you the result. The other concept in LangChain is tools, and here is what we were mentioning before. For instance, you want the LLM not to do calculations itself, but you want to delegate that into some other calculator tool, or the LLM does not have knowledge about recent events because it was trained with data from 2 years ago. So you want the LLM to be able to search something. So you have a search tool. So all these things are represented by tools, and there are many of them that are already available for you in LangChain, and you can just use them. Or also you can just create your own tool by simply defining a small function, and then you just call that function. So again, LangChain takes care of all the mechanisms to send the LLM the description of the tool and all the things that are needed, so you can use it more easily. And the final concept is the agent. An agent can make decisions based on the output of the LLM. The core idea of the agent is to use the LLM to choose a sequence of actions to take. So the difference between a chain and an agent is that in chains, the sequence is hard-coded, whereas an agent can define, okay, if this was the answer of the LLM, if it contains these words, then do this. If it contains these other words, do that. For instance, if you ask the LLM and the LLM says, I need to calculate this, then you can invoke the calculator. If the LLM answers, I need to call this function, you can do the actual invocation of the function with the parameters. Let's say in Python, you return that, and then you feed that back to the LLM. So the agent is a kind of a generalization of the pipeline, which can invoke flexible actions. And there are many agents available, and some of the names you will recognize, Zero Shot and Structured, and they are conversational, and there is the OpenAI functions one, and so on. As an example, a React agent is an agent that allows you to do different things depending on the output of the language model. And here we said, okay, load these tools. These tools are predefined in LangChain, so you don't have to create them. It's called LLM Math and Search API. Here is an example from LangChain, who is Leonardo DiCaprio's girlfriend, and what is the current age rise to the 0.43 power. Why would anyone ask this? I have no idea, but this is an example of how to use different tools. So the model says I need to find out who's this person's girlfriend is. it searches that, and the observation here is the answer from the tool. So the tool executes a search, it comes back and it says, okay, this is the observation. So you insert that into the LLM and you send it back. And here's another thought. I need to find this person's age. Again, search, and the answer is the observation here. And here's the thought. I need to calculate this. So you do the calculation, you send it back, and here's the observation. And the LLM finally answers, I know the final answer. It's the number here. So you can see how the LLM is not a one API call interaction, it's several of them. And then the tools are used, the information is retrieved, numbers are calculated, and they're sent back to the LLM. And finally, the LLM answers with the final response. And again, if you want to do the same, instead of using the React, you want to use it using the OpenAI functions, you do something very similar for this exact same example, which again is from the LangChain website. And you define the tools in here. You have a search tool, you have a calculator, and which again, these are functions that are already provided by LangChain. And there's a foobar DB. The idea is to show how this tool is not used in the example. So they start with the same question here, and then invoking search with this query, there's an answer, and then the expression is calculated, and here's the answer, the final answer from the model. Again, this is two ways of the model using tools to generate an answer. But the key concept here is that the model can use tools to gather more information. And so it's not limited, it's not fully limited to what the training data was. You can insert small pieces of information as long as they fit into the prompt and tell the model to infer from there. Now, searching the relevant pieces of information, if you have some documents or you have a lot of data, could be non-trivial. So one of the frameworks that people often use are vector databases. A vector database is just exactly what it sounds like. It's basically a database where instead of tables, you store vectors of numbers, and you say, the query is give me the vector that is closest to this one, and it answers with a list of vectors that are closer to that one. And the idea is that in those databases, you store vectors, which are embeddings, and those embeddings are used to retrieve relevant information. So for instance, if you have a series of documents, let's say you have some PDF documents, many of them. Obviously, if this is your relevant information, it might be very long and it might not fit in the prompt. So what you do is you split these documents. Maybe you grab a document and paragraphs, and from these paragraphs, you create an embedding, and this embedding vector, you create many of them because you scan through all the documents. For each paragraph, you create embedding vectors, and these embedding vectors get stored in the database with a proper link back to the document. Then let's say you have a prompt here and you want to look for some relevant information. You grab this and you also pass it through the embedding model, and you get a vector of numbers, and you search with that vector in the vector database, and it retrieves the similar vectors and the corresponding text or the links to the document. You select from that and you put it back into the prompt, and you send that relevant information to the language model. So you only send the language model the relevant information, and the way you search for that is using a vector database. This is called retrieval augmented generation. And perhaps if you notice that here in one of the examples there's one called document store as well. And also when we talked about one of the retrieval augmented generation. So this technique is having information in some database, and you somehow retrieve that information and you feed it to the prompt. This is a figure from the paper where this was first introduced. The idea again is to make sure that you can augment the LLM with some search, and you don't need to fine tune it for this specific knowledge. You just search the database for a very specific parts of information from your documents, and you insert those specific items into the prompt. In a nutshell, a vector database is basically you have some content, like I mentioned before, which could be a set of documents. You have an embedding model, you run it, and you create vector embeddings, and you put those vector embeddings in the database. Here, they're shown as dots in some two-dimensional space. When you have your application, you do a query. You again pass it through the same embedding model. You have a vector embedding. And let's say that this is your query. You search for all the elements that are close within a radius. And those are the ones that are relevant to your search. This is the key. This is the basic concept of a vector database. Sometimes what happens is that you prompt the language model to extract or formulate a question based on the prompt. Instead of extracting directly from the prompt, you tell the language model, formulate a question based on this, and you send that question to the database. Now, when you have the documents here, you might have several documents that are similar to your query. So how do you deal with having several documents? Because you might not be able to put all the documents in the prompt. So there are several techniques for that. Two of the most common techniques are the refine techniques, where you ask a question and you have some documents, and then you tell the LLM to summarize it, and it creates a document, and then you grab another document that says summarize this too, and creates another summary, and so on until you have only one refined answer. Another approach is map reduce. This is basically the same. You have several input documents, and in this case, you ask the LLM to generate an answer for each of them, and then from those answers, you say, okay, collect these answers and combine them into just one sentence, and it gives you one answer for that. So you use the LLM to do a summary of all your documents or to do a summary of all your answers. These are two standard techniques. In the last few minutes, I don't think we have a lot of time to go into that, into this, but it's about scaling inference and training. I'm going to have to skip very quickly through this because we don't have enough time, but there are basically several techniques. One typical one is to reduce the size of the floating point numbers. Instead of using 32 bits, you use 16, or you quantize it even farther using 8 bits or even 4 bits in some cases. When you use multiple GPUs, there's an NVIDIA library that allows you to send information between GPUs. So when you're scaling to multiple GPUs, there are several techniques. One is called DDP, where you start the process in several GPUs, assuming the model fits in those in one single GPU. You just run the training on several GPUs. Each GPU receives different data. It does the forward pass, it does the backward pass, and then during the backward, the gradients are averaged and then spread across the GPUs. So all the GPUs have the same model. There's another one called Zero. It's a little bit more complicated. I don't think I have time to explain, sorry, but there are many techniques related to parallelism on different GPUs, and each of these techniques, some have different types of problems, like creating bubbles of usage and so on. Then people try to optimize those with other techniques with different degrees of success, making better usage of the GPUs. Tensor parallelism is simply spreading the tensor multiplications across different GPUs. Then you can start combining data parallelism with pipeline parallelism, and you get really crazy. I apologize that I didn't have time to go into the details of this. That's all I have for today.